Hello, this is David Wethey. I'm going to talk about our poster on calibration of ECOSTRESS and biocorrection by comparison with hyperspectral sounder data. My collaborators are Sarah Woodin and Jorge Vazquez. ECOSTRESS is an instrument on the International Space Station. It's a push-whisk radiometer with 3 active infrared bands. Pixel size is 69 by 69 meters, and it has a swath width of about 400 kilometers. Scene sizes are 5400 by 5632. It has a revisit interval daily at high and high latitudes and 5 days at the equator. And it is archived by USGS LPDAC, and it serves as a precursor to the Trishna SBG and LSTM missions. The cross-track infrared sounder is on the SWOMI NPP satellite and JPSS 1 and 2, and it's a completely different form of infrared device. It's a Michelson Fourier transform spectrometer. It has 717 channels between 9 and 15 microns, and it has a really big field of view, 14 kilometer oval to circle field of view. The swath width is 2,200 kilometers, and radiances are traceable to the National Institute of Standards and Technology. And it has a revisit interval of 2 times per day because it's on polar satellites. And it's archived by NASA Goddard Space Flight Center. So why do we need to calibrate ECOSTRESS? Well, ECOSTRESS Collection 1 skin temperatures have a 1.13 Kelvin median cold bias versus in situ. So here's in situ equam temperatures from NOAA, and here's the retrieved surface temperature from ECOSTRESS. The 1-to-1 line is the dotted line, and you can see that the points lie below the line and are pretty much parallel to the line. This is a data set where I use best quality equam, best quality geosynchronous collocations for cloud cover removal, and then robust outliers were removed. So overall, there's a 1.13 cold bias, but also there's non-uniformity in the focal plane that causes biases. So here is the brightness temperature anomaly on the 10.49 micron channel versus pixel number in the focal plane. There are 128 pixels in the focal plane, and you can see that the right-hand edge of the focal plane, pixels 120 to or 100 to 128 tend to be lower brightness temperature than those in the middle. And then there's also a fall off at the other end. And so it's sort of a parabolic relationship here between pixel number and bias. What this leads to is striping in the retrieved images and checkerboard artifacts, because when geolocation is done, because there are overlaps from adjacent swaths, the pixels on one end of the focal plane end up being geolocated next to retrievals from the other end of the focal plane. And so then you have cold and warm pixels that are lined up next to each other, leading to this checkerboard pattern, which is not possible in an ocean environment. So there's an overall bias, and then there's non-uniformity across the focal plane. So we used quasi-simultaneous overpasses, acquisitions within 30 minutes. ECOSTRESS scenes were in the middle of the CrIS track. So here's the CrIS track. These are the fields of view. And here's an ECOSTRESS scene that's in the middle of the CrIS track. And here's an example field of view that was used. It has a low standard deviation among the retrieved brightness temperatures within the field of view. So there are about 30,000 ECOSTRESS pixels in here with a standard deviation of 0.38 Kelvin. So the sounder radiances were used as a reference standard. So every one of those fields of view retrieves a spectrum, and these were convolved with the spectral response of 2 of the ECOSTRESS channels. The third channel is not possible to use because the CrIS sounder doesn't go that low in terms of wavelength. So then we end up with convolved radiances. These are then integrated, and then the brightness temperatures are calculated with the Planck function. So we looked at radiance bias and brightness temperature bias and compared those to the ECOSTRESS retrievals. So here is an example of the result. Here is the ECOSTRESS radiance on the horizontal axis and the radiance from the CrIS hyperspectral sounder on the vertical axis. The one-to-one line is a dotted line. Here's the 10.49 micron band. Here's the 12.09 micron band. And in both cases, the data from CrIS has higher radiances than the data from ECOSTRESS. And the radiances tend to be are very well correlated, R squareds of 0.99 approximately, with 20,000 collocations between CrIS and ECOSTRESS. Now, what's interesting is that the ECOSTRESS engineering team has produced two versions of ECOSTRESS data. Collection 1 is the original, and Collection 2, they did a bias correction on the retrieved radiances to try to correct the 1.3 or 1.13 Kelvin retrieved temperature bias. The regression equation that they used is the blue line here, and what we notice is that at high radiances, the CrIS data lie above that line, and at lower radiances, the CrIS data lie below that line. So the correction that JPL applied does not appear to actually reflect radiances that are retrievable at the top of the atmosphere. So it suggests that the corrections in collection 2 aren't really doing the job completely, and further correction is necessary in order to get good retrievals. If we look at the non-uniformity across the focal plane, I've calculated the correction factors, gain and offset, to convert the collection 1 radiances to the equivalent CrIS retrieved radiances. And what we see is that there's variation across the focal plane, but there's also variation among years. Now, what's interesting is the gain that's supplied by JPL in collection 2 is down here. So this is gain on the vertical axis from 0.95 to 1, and then pixel number in the focal plane from 1 to 128. Here then is the offset on the regression equation. The JPL collection 2 offset correction is here, but the values that are calculated based on the retrievals, the retrieval comparisons between ECOSTRESS and CrIS give one this set of numbers. So the JPL collection 2 offset correction and gain correction don't seem to match the data that one gets with an on-orbit comparison. The way ECOSTRESS collection 2 correction factors were derived was by comparing the retrieved brightness temperatures with expectations based on in-situ data on the ground, both in Lake Tahoe, the Salton Sea, and then various desert sites. But the comparison is that CrIS is making a comparison of radiance retrieved in orbit between two different instruments: radiance retrieved in orbit via the hyperspectral sounder, and then radiance retrieved by the mercury cadmium telluride detector in ECOSTRESS. And that, we feel, is a better method for doing calibration than the comparison with in situ. We're also seeing some long-term sensor drift. The bias at the beginning of the record in 2019 is on the order of -1, and it's a little bit more than -1 brightness temperature bias by the end of 2023. And it's that bias change is about 29 millikelvin per year. We also see a trend with solar elevation, both in day and night. So solar elevation on this axis, solar elevation below the horizon on this axis, and we see a trend that at high solar elevations during the daytime, the bias gets to be as low as 0.75 Kelvin, and at when the sun is at the horizon, the bias is down at about -1.25. So that suggests that there's perhaps some kind of a thermal effect on the space station. As the space station itself and the instrument is heating, the bias seems to be changing. So we may be able to track that down by through the engineering data once those data become available. Thank you very much.